physical quantities and what are the different uses of dimensions. In today's lecture, we are going to study different errors in measurements. Faulty measurements of physical quantity can lead to errors. Errors are broadly divided into two categories: systematic errors and random errors. Let us first study what are systematic errors. Systematic errors are the errors that are not determined by chance. They are usually caused because of faulty instruments and wrong experimental techniques used by the observer. Systematic errors are those errors which can be eliminated or minimized. Systematic errors are further divided into three categories. First is instrumental error. It is an error which is caused due to faulty instrument. For example, if we are making use of weighing balance in a laboratory to measure the weight of an object, the pointer of the weighing balance in the laboratory is already indicating some value instead of showing 0 when no load is kept on it. So in such a situation, all the readings which will be taken, there will be some error in measurement. Such kind of error which is introduced because of faulty instrument is called as instrumental error. Second type of systematic error is error due to imperfection in experimental techniques. This is an error due to defective setting of an instrument. If the instrument is not properly set before starting the experiment, there could be error in measurement while taking the readings. For example, the measured volume of a liquid in a graduated tube will be inaccurate if the tube is not held vertical. So, the error which is caused over here is due to imperfection in experimental techniques. This error can be eliminated by changing the experimental techniques. So such error comes under systematic error. The third type of systematic error is personal error. Such errors are introduced due to the fault of the observer or the carelessness of the observer. For example, while measuring the length of an object with a ruler, it is necessary to look at the ruler from directly above. If the observer looks at it from an angle, the measured length will be wrong due to parallax. Such kind of error due to the fault of the observer is called as personal error. So all of these three errors come under the topic systematic errors because all of these errors can be eliminated. So systematic errors are those errors which can be eliminated and which are caused by faulty instrument or wrong experimental techniques by the observer. There are three types of systematic errors, that is instrumental error, the error which is introduced because of faulty instrument. Second one, error due to imperfection in experimental technique. It is introduced if the experimental technique is wrong. And the third type is personal error. This error is caused due to the carelessness of the observer. So systematic errors can be minimized by using proper instruments, by following proper experimental techniques, and by removing personal errors. But even after all of these things are done, there are some errors which cannot be removed. Such errors which cannot be eliminated are called as random errors. For example, if we are performing an experiment related to electricity, the voltage of the power supply may change randomly. So this error which is introduced over here is cannot be eliminated by the observer. So such error will be called as random error. Random errors cannot be eliminated, but they can be minimized by repeated observations. So instead of taking the reading once, we can take readings many times and then take the mean of the reading. So let us see how to take different readings and how to find the mean of the readings. Suppose the readings recorded repeatedly for a physical quantity during a measurement are A1, A2, A3 up to AN. So we are taking the readings for a same physical quantity, not once, but we will be taking the readings n times. And the readings which we get, we will be naming it as A1, A2, A3 up to AN. The arithmetic mean, A mean, is given by, we already know the formula for mean. So over here, the mean of all the readings will be given by A mean, which is equal to A1 plus A2 plus A3 up to AN divided by N. This A mean is the most probable value of the quantity. So we have taken so many readings for the same quantity, out of which A mean will be the most probable value of the quantity. Now each value over here, we will be finding out how much is the error in measurement of each value of each reading over here. So A1, for A1, the absolute error is the error in calculating A1. So the absolute error delta A1 is given by delta A1 is equal to modulus of A mean minus A1. So this much is the difference between the most probable value and the first value, the most probable reading and the first reading. This difference is called as absolute error for reading, for the first reading, that is A1. For the second reading, the absolute error in calculation of the second reading, that is A2, will be denoted by delta A2, and it is equal to modulus of A mean. A mean is the most probable, most correct value out of all of these, minus the second reading. This modulus sign indicates that even when we subtract it and if the answer comes out to be negative, still we will be taking it as positive because we just want the difference. We don't want if it is positive or negative. So similarly, we can calculate the absolute error for each and every reading over here up to AN. And so for AN it will be the absolute error for A1 is delta AN is equal to modulus of A mean. A mean is the most probable value minus AN. So this is the formula for absolute error of individual readings. Now let us find out the arithmetic mean or the mean of the absolute errors. So we have found out absolute errors for all the readings, that is delta A1, delta A2, delta A3 up to delta AN. Now we have to find the mean of this absolute error. Mean of this absolute error is given by delta A mean, which is equal to delta A1 plus delta A2 plus up to delta AN divided by the total number of readings, that is N. So this A mean is the most probable reading out of all of these, and delta A mean is the error that is caused while measuring A mean. So the measured value of physical quantity A can be represented by A is equal to A mean plus minus whatever is the error, that is delta A mean, which tells us that the actual value of A could be between A mean minus delta A mean and A mean plus delta A mean. So the value of A will range in between these two numbers because A mean is the most probable value but not necessarily the correct value. So it can range in between this value A mean minus delta A mean up to A mean plus delta A mean. The ratio of mean absolute error, that is delta A mean, to its arithmetic mean, that is A mean, is called as relative error. So the formula for relative error is whatever is the error, that is delta A mean, divided by whatever is the probable value, that is A mean. Now let us find the percentage error. For finding percentage error, you have to multiply relative error by 100. So percentage error is equal to relative error. Relative error is given as delta A mean divided by A mean multiplied by 100. So now we will be solving a numerical by using all of these formulae. The radius of a sphere measured repeatedly yields values 5.63 meter, 5.54 meter, 5.44 meter, 5.40 meter, and 5.35 meter. So the radius of a sphere is measured many a times, and we have got these 5 different readings. We have to determine the most probable value of the radius and the mean absolute error, relative and percentage error. Now the most probable value of the radius is nothing but the mean. So the formula for arithmetic mean is adding all the readings and dividing it by the number of readings. So we have added all the readings over here and there are 5 number of readings. So we will be dividing it by 5. After solving this, we get the answer as 5.472 meter. So the radius of the sphere is approximately and very close to 5.472 meter because it is the mean of all of the readings which we have got. The next thing is to determine mean absolute error. Before determining the mean, let's first find absolute error for all of these individual readings. The formula for absolute error was modulus of individual reading. Let's take the first reading minus the mean reading. The absolute error for the second reading is modulus of the second reading minus the mean. The absolute error for the third reading is the third reading minus the mean, and the absolute error for the fourth reading is the fourth reading minus the mean. Absolute error for the fifth reading is the last reading minus the mean. To find mean absolute error, we will be adding all the individual absolute errors and dividing it by the number of readings. The total number of readings are 5. So we will be dividing it by 5. So this modulus sign indicates that when these two numbers are subtracted, even if the answer comes out to be negative, still you will be writing it as positive. After solving this, we get the mean absolute error as 0.0904 meter. So this is the value which is most close to the actual value, and this much is the error in the measurement of this value. The formula for relative error is equal to the mean absolute error divided by the mean value. So 0.0904 divided by 5.472, which is equal to 0.017. And percentage error is, we will be just multiplying this relative error by 100. So when you multiply this by 100, this decimal point shifts 2 times because it is multiplied by 100. So it will come as 1.7%. The next topic that we will be studying is significant figures. To understand this topic, let us consider an example. If we are measuring the length of a metallic rod by using a meter scale, the least count of a meter scale is 0.1 centimeter. Least count of any instrument is the smallest reading that the instrument can take. So when we have a meter scale, the smallest reading that scale can take is 0.1 centimeter. So we are making use of meter scale to take the length of a metallic rod. First, when we take the reading, it comes out to be as 15.4 centimeter, and again when the reading is taken, it comes out to be as 15.5 centimeter. When we take the mean of these two readings, it comes out to be as 15.45 centimeter. So significant figures are the figures which are there when the reading was taken. So over here there are 1, 2 and 3 figures. So in this readings there are 3 significant figures. Even if the mean comes out to be as 4 figures, 1, 2, 3, 4, still the significant figures out of these are only the first 3 figures. So let us define what are significant figures. The number of digits in the measurement about which we are certain about these 1 and 5 digits over here, plus one additional digit, the first one about which we are not certain. So we are not certain about 4 and 5 because it is changing over here. But we will be taking this 4 because it is the first not certain digit. So over here there are three significant figures. So significant figures are defined as the number of digits in a measurement about which we are certain, plus one additional digit, the first one about which we are not certain. There are some rules while determining the significant figures. Let's check the first rule. All of the non-zero digits are significant. For example, if we are measuring the volume of the object and if it comes out to be as 178.43, all of these 5 digits over here, that is 1, 7, 8, 4 and 3, are significant digits because they are non-zero digits. Second rule for determining significant figures is that all the zeros between two non-zero digits are significant. Example, if the mass of the object is 165.02, this zero lies between two non-zero digits, so this zero also has to be considered as significant digit. So in this reading, there are total 5 significant digits: 1, 6, 5, 0 and 2. Total 5 number of significant digits. So the third rule in determining the significant digits is that if the number is less than 1, the digits which are on left hand side should be considered as non-significant. So in this example, there are 4 significant digits. The zeros which are to the left hand side should be considered as non-significant. So over here 1, 4, 0, 5. Total 4 number of significant digits. And the last rule in determining the significant figures is that the zeros on the right hand side should be taken as significant figures. So we have a number like this, 1.500. So total number of significant figures over here are 4 because 0 are on the right hand side and should be considered as significant. So over here, if you take these as, or let us take one more example as 0.01500. So the zeros which are on right hand side should be taken as significant. The zeros which are on left hand side should not be taken as significant figures. So in total there are 1, 2, 3, 4 significant figures. So these are the rules while determining the significant figures. First rule is that all of the non-zero digits should be considered as significant. Second rule is that if there is 0 in between two non-zero digits, that 0 has to be considered in significant digits. If the number is lesser than 1, the zeros which are to the left hand side should not be considered as significant. And the fourth rule is that if the zeros are on the right hand side of other digits, then they have to be considered as significant digits. All of these 4 rules has to be kept in mind by determining the number of significant figures. The next topic that we will be studying is order of magnitude. The magnitude of any physical quantity can be expressed as A into 10 raised to n, where A is the number such that A should lie in between 5 and 0.5. So A should be lesser than 5, but it can be equal to or it can be greater than 0.5. And n is an integer and n is called as order of magnitude. Now let us understand this definition of order of magnitude by giving few examples. The radius of the earth is equal to 6,400 kilometers. You have to write this number in the form of a into 10 raised to n to determine order of magnitude. So let's write this number in the form of a into 10 raised to n, and a should be between 5 and 0.5. It should not be greater than 5 or not lesser than 0.5. So if we want to convert this number into meter, this kilometer can be written as multiplied by 10 raised to 3. So the number will be 6400 into 10 raised to 3 meter. Always convert it into SI unit. So kilometer has to be converted into meter because meter is the SI unit of length. So when we convert 6400 kilometer into meter, it will come as 6400 into 10 raised to 3 meter. And after shifting the decimal point to the left hand side 1, 2, 3 times, it will come as 0.64 into 10 raised to 7 meter. So over here the order of magnitude is 7 and the number of significant figures is 2. Let us consider one more example as magnitude of charge of an electron. Over here, the magnitude of charge is 1.6 into 10 raised to 19 coulombs. This number is in between 0.5 and 5. So we don't have to make any changes over here. So over here, order of magnitude is minus 19 and number of significant digits is 1 and 2. So in order to find order of magnitude, we have to convert the number in the form a into 10 raised to n. Over here, n will be the order of magnitude. And a always has to be a number which is lying in between 5 and 0.5. It should not be greater than 5. It can be equal to 0.5, but it should not be lesser than 0.5. So it can lie in between 0.5 and it should be lesser than 5. So over here we have seen the radius of the earth. We have to convert this number in this form such that first a should be in the range of 0.5 up to 5. So firstly we will be converting this kilometer to meter and then changing the number in such a way that the number which we are writing is in between 0.5 and 5. 0.64 will lie in between these two numbers. Multiplied by, we are getting it as 10 raised to 7. So whatever is the power will be called as order of magnitude, and over here the significant figures are only 2 because 0 is on left hand side. We will be not including the 0. The order of magnitude is 7 and the number of significant figures is 2. In the second example, already the number which is given 1.6 is in the range of 0.5 and 5. It lies between 0.5 and 5. So we don't need to make any changes over here. So over here the order of magnitude, that is power, is minus 19 and the significant digits are 1 and 6. That is total 2 number of significant digits.